Hi, and very good morning. We are from Group 7, Group SLE, and today we are excited to present our numerical app, which is the Composite Quadrature rule and the Trapezoidal versus Simpson rule. Okay, before we dive into the details, let us introduce our group members. Okay, so firstly we have SOOPIETCIERA, NAZIRUL HAKIM, MUNIRAH, and then ZUBAIR, and lastly Adam ZIKRY. Okay, so let's start our presentation. Okay, as you can see in this slide, this is a comparison between trapezoidal versus Simpson. Okay, this is a basic idea what we did in this numerical app. Okay, so for trapezoidal, it approximated the area of under a curve by dividing it into a series of trapezoids. Okay, so the rules is that we assume that the curve between two consecutive points is a straight line, and then calculate the area of each trapezoid and sums them up into to obtain an estimate of the integral. Okay, so for Simpsons, this method takes a slightly different approach. Instead of dividing the curve into trapezoid, we divide it into a series of parabolic segments and then assumes that the curve is well approximated by this parabolic segment.
Now, let's discuss our findings. This is our app. For this tree, it requires user to enter the input. We use this coding to obtain the integration of the trapezoidal and Simpson's rule. For some function, we have to use dot, especially for multiplication and power, as you can see here. While to enter the input for the limit, user need to enter the lower limit first. After that, the upper limit. Don't forget the bracket. To obtain the output for composite trapezoidal, we use this coding, which will display the result in the output area. And for Simpsons, we use this two line of coding to display the output. Matlab will process this code to calculate the integration of function by trapezoidal rule, and this code for Simpson's rule.
Here is the coding for output for approximate integral using trapezoidal rule, and here is the output for composite Simpson rule, and here is the error that calculated by trapezoidal rules, and this is error that calculated by Simpson rule, and this is the exact integral. And as you can see here, Simpson error is less than trapezoidal error. So, from here we can conclude that Simpson error is more accurate than trapezoidal error. And here you can see the function graph. So, let us look at the code view. In the code view, this is the code that we calculate approximate integral using trapezoidal rule. And this is the code that we use to show the graph. And this is the how we calculate the error, that is exact value minus integral value. This is the code that we calculate approximate integral using Simpson rule, and the code for exact value is here, and it was calculated by using our function and our limits that user input.
So, in conclusion, as we observe from the previous part, okay, so we can conclude that the Simpson's rule provide more accurate result compared to the trapezoidal rule. Okay, this is because due to the fact that the trapezoidal rule assumes a straight boundary between the ordinates, which limits its accuracy. On the other hand, the Simpson's rule takes into account that the curvature of the boundary, resulting in greater precision when the curve is convex or concave towards the baseline. Okay, that's all from us. Thanks for your attention, and we hope that our presentation will meet your expectation and contribute to a successful evaluation. Thank you.